Okay, my friends, let's look at another example on curve sketching using the first and second derivatives. And this is all about intervals of increase, decrease, all this good stuff, intervals of concavity, and a sketch. Let's suppose that our function was 5x to the 2/3 minus 2x to the 5/3. Five x to the 2/3 minus 2x to the 5/3. So, step one, find the critical numbers. This is going to be where f prime equals 0 and where f prime is undefined. So we need f prime. Here we're going to have 2/3 times 5 times x minus 3. 2 minus 3 is to the minus 1/3 minus 2 times 5/3 x minus 3 to the 2/3. So in other words, we got 2 times 5, 10 over 3 times the third root of x. Hold on a second. I'm actually going to do this with exponents because it's going to be easier to factor it in a minute. It's true what I wrote there, but when it comes to factoring, go ahead and just leave everything in exponents. So we got 10/3 x to the negative 1/3 minus 10/3 x to the 2/3. So this is a little factoring thing that you should know. You can always factor out the x of least degree. In other words, I can factor out an x to the negative 1/3 here. I can factor out a 10/3 because there's 10/3 in both terms, and I can factor out the x of least degree, which is x to the negative 1/3. So that's what I've factored out. Well, that just leaves me a 1 in the first term. And now I'm going to have some power on an x right here. Because the 10/3 x to the negative 1/3 times 1, there's your 10/3 x to the negative 1/3. And when that distributes in there, the 10/3 is going to be taken care of. And I need an exponent on this x. So that when I multiply x to the negative 1/3 times x to that exponent, I get x to the 2/3. In other words, I need something when I add it to negative 1/3, I get 2/3. Kind of a little bit of an aside here is I need to figure negative 1/3 plus what equals 2/3. Because remember, when I multiply those x's, I'm going to add the exponents. So whatever exponent I have right here, I'm going to be adding to negative 1/3. And when those multiply together and I add those exponents, I need to get x to the 2/3. So that's why I'm taking negative 1/3, I'm adding it to some unknown exponent, and I'm getting 2/3. So you can solve this by adding 1/3 to both sides and getting that the exponent that we need is 2/3 plus 1/3, otherwise known as 3/3. So look, x to the 3/3 is going to be what I need here. Because when this distributes into that second one, it's going to be negative. It's going to be 10/3. When I add the negative 1/3 plus the 3/3, I'm going to get x to the 2/3. So there it is. Of course, 3/3 is just 1. So this really just says 10/3 x to the negative 1/3 times 1 minus x. You got to be able to factor this. Because don't forget what we're doing. We're taking that first derivative and we're setting it to 0. And finding where is it undefined. So now I'm going to want to write this as a fraction because it's going to be a little easier to see what's going on. Here's a fraction bar. We got a 10 upstairs. We got a 1 minus x upstairs. We got a 3 downstairs. And we got a third root of x downstairs. There's that first derivative. Now I want to know, if you remember, I want to know for critical numbers, I want to know where is f prime equals 0 and where is f prime undefined. So I want to know where is this equal 0? A fraction only equals 0 when the top is 0. In other words, when 10 times 1 minus x equals 0. That's going to happen when 1 minus x equals 0. That's going to happen when x equals 1. Also for critical numbers, and this is the first example we see like this, I also want to know where is f prime undefined. So where is f prime undefined? This is going to happen when the bottom equals 0. That's going to happen when the third root of x equals 0. In other words, that's going to be when x equals 0. So these are the critical numbers of my function. The critical numbers of this function are x equals 1, that's where the tangent is horizontal, and x equals 0, that's when the tangent is undefined. So that was all kind of step one, just like we do in all these things. We find where is the first derivative 0 and where is the first derivative undefined. So now I want to go and play the first derivative game. See if I can still do that over on the side like I like to do here. Let me move this over a little bit. And in step 2, I want to do what's called the first derivative test. I want to put those critical values on a number line, x equals 0 and x equals 1. And I want to choose test values that are in the domain of the function in each of these intervals. Less than 0, between 0 and 1, and greater than 1. So something less than 1, if it's in the domain, which it is, because by the way, look at our function. The domain is all real numbers here, because we're taking third roots, and we can take third roots of anything. So I would test then, just to make the arithmetic as easy as possible. You can test any number you want. You can choose negative a half, negative a tenth, negative 3, negative 10, negative 37, whatever you want. I'm going to test negative 1. Now I need a test value between 0 and 1. I'll test a half. Now I need a test value greater than 1. I'll choose to test 2. So we're sticking these into the factored form of the first derivative. Since that's a little off the page over there, actually it looks like I got enough room to slide this over here. Let me see if I can go a little bit over more, and we can keep an eye on our first derivative. I would just look at the factored form of the first derivative right here. I like to look at the factored form of the first derivative. You could look at, to tell you the truth, I would say where I've written it as a fraction might be a little nicer. You could do what I just did, but on second kind of glance, it's going to be easier to stick those test values right in here into the factored form that's in fraction form. So I'm going to stick negative 1 into here. Well, the 10 is positive. Now I'm sticking in x equals negative 1. 1 minus a negative 1 is 1 plus 1 is positive. Over the 3, which is positive. And now I'm taking the third root of negative 1. Well, the third root, an odd root of a negative number is negative. So I got a positive times a positive up top, which is positive. And I got a positive times a negative on the bottom, which is negative. So I got a positive over a negative, which is negative. So what I've determined here is that the first derivative is negative when we're to the left of 0. When the first derivative is negative, all tangent lines have negative slope. In other words, the function is decreasing. So now be very careful about this, because at x equals 0, you might make a mistake and think that we have a horizontal tangent. But at x equals 0, that was a value where the first derivative is undefined. And when the first derivative is undefined, we don't have a horizontal tangent. We got something weird going on there, like a point or some kind of a vertical tangent. So usually what I'll do there is I'll just kind of put like a, definitely don't put a little horizontal tangent there. I'll put like a little dotted line or something. There's either an asymptote or a point, something funny going on there. We're not sure what yet. So now we go on to our next test value, which is a half. So I'm looking at the form of the derivative right where my finger is over here on the left, and I'm sticking in a half. The 10 is positive. The 1 minus a half is positive. The 3 is positive. The third root of a half, I don't care what it is, I just know that the third root of a positive number is positive. So we got a positive, positive over a positive, positive. We got a positive over a positive, which is positive. When the first derivative is positive, the function is increasing, so I know the function is increasing past there. Now we're at this value 1. Well, at x equals 1, that's a critical number that caused the first derivative to be 0. So in that case, we do have a horizontal tangent at 1. So I'll sketch it right in there like this. Now we're at 2, the test value 2. So we got 10, which is positive, 1 minus 2, which is negative, 3, which is positive, and the third root of 2, third root of a positive number, is going to be positive. So I got a positive times a negative on the top, which is negative. And I got a positive times a positive on the bottom, which is positive. A negative over a positive is negative. So that tells me when the first derivative, that tells me the first derivative is negative. And when the first derivative is negative, all tangent lines look like this. In other words, the function is decreasing. So we got a lot of information right here about what this graph looks like. And I can show you the trick on this. The deal is, let me just kind of like scoot this paper down so we can do a little something on the side right here. If the graph is decreasing to some undefined tangent and then increasing on the other side, that's when it's going to look like this. Right here. I can tell you just from experience, and we'll see this when we check concavity, it's going to be concave down on both sides of this 0. It's coming down to a weird little point right there. Okay? So something we could check is, you know, when x is 0, what is the y value? So I'm looking up here where my finger's up on the upper left, and I'd like to know, what's the y value when x is 0? This is 0 minus 0. The y value is 0. So this point is 0, 0. In other words, this little cusp right here is at 0, 0. That's what the graph looks like right there around 0. Now right here at 1, this is called a local max. And it's right up here. I usually just sketch it right on the first derivative like I'm doing. I know that the x value is 1. Now I'd like to get the y value. So I'm going into the function. If x is 1, this is 5 times 1 minus 2 times 1. 5 minus 2 is 3. So this is at 1, 3. So I've got a lot of information about what the graph looks like already, but I still need to get the intervals of concavity, so that's where I use the second derivative. So let's get on with that now. Let me see here if I got a little bit of room to do this right over here. Now I want the second derivative, right? So let me see if I can get all this on one page. See how, I mean, if I wanted to, I could use the first derivative written like this and use the product rule, or I can use the first derivative written like this and use the quotient rule. They're both really just as, one is just as easy as the other. I know a lot of you want to go to the product rule. I would just use the quotient rule right here. So now I'm doing f double prime of x, right? Because this is where we need concavity. The second derivative is used to talk about concavity. So then I got low, which is 3 times x to the 1/3 minus low, oops, I got low 3 times x to the 1/3 d high, which is going to be 10 times the derivative of this is negative 1 minus high 10 times 1 minus x d low. Let me get rid of this little bit of line right here. D low, which, hold on a minute now. Did I go low, D high, minus high? Now I'm going D low. 3, and now the derivative of x to the 1/3 is 1/3 x to the negative 2/3. We'll check that like I always double check everything in a moment, but now don't forget to square the bottom. So when I square the bottom, I square the 3, which becomes a 9, and I square x to the 1/3, which becomes x to the 2/3. So did I go low, 3x to the 1/3, d high, 10 times negative 1, minus high, 10 times 1 minus x, d low, 3 times the derivative of x to the 1/3, which is 1/3 x to the negative 2/3. And then square the bottom, 9x to the 1/3 squared is x to the 2/3. So we're going to end up having to set this to 0 and find where it's undefined. So you're going to need to factor it. You're not going to be able to avoid it. So let's start simplifying this. A couple steps here. Here we got a 3 times 10, which is 30, and we got a negative 30. So we got negative 30 x to the 1/3 minus the 3's cancel here, and we got a 10, and we got a 1 minus x, and we got an x to the negative 2/3. And this is all over 9x to the 2/3. So we're simplifying it as we go here. So now then, it's time to factor this thing, because what we're going to want to do is set it to 0, and the only way you're going to do anything intelligent with this thing set to 0 is to factor it, as I keep saying again and again through the whole quarter. We can definitely take out a negative 10, because there's a negative 10 common to both those terms. We're just looking at the numerator, and we can take out a negative 10 out of the numerator. Now, like I was saying earlier, you can always factor out the x of least degree. So we can take out the x to the negative 2/3. And you're going to need to do this. It's not like you can, it's like you have to. So we took out the negative 10, we took out the x to the negative 2/3, and now that's our greatest common factor and out of the numerator, and now we want to see what do we have left. Well, the negative 10 is going to multiply by a 3, and I need some power on an x, so that when this x to the negative 2/3 multiplies this x to some unknown exponent so far, when I add those exponents, I'm going to get 1/3. See how this exponent wants to be a 3/3? Because when I take the negative 2/3, when I multiply these powers of x's, the exponents are going to add. And when I take the negative 2/3 plus the 3/3, that's going to give me x to the 1/3, and that's what I needed right here. So that's all set. Now, I took out the negative 10, I took out the x to the negative 10/3. All we have left in that term over there is a 1 minus x. So this is actually a plus 1 minus x. We'll look at that again in a second, but it's over 9x to the 2/3. You got to be able to factor these things. They're really not bad, of course, if you practice half a dozen of them, like I'm always saying. When I distribute this into the first term, the negative 10 times the 3 is going to be a negative 30. The x to the negative 2/3 times x to the 3/3, the exponents are going to add. I'm going to get x to the 1/3. This thing's going to now distribute in the second term. The negative 10 times the plus over here is going to give me a negative 10. And when I take, and I got a 1 minus x, there's the factor of 1 minus x, and the x to the negative 2/3 is right there. So this thing's factored. So now we're just about there with this thing. We've got a negative 10 x to the negative 2/3 times 3x to the 3/3, otherwise known as 3x. See how we got a 3x minus x? Well, 3x minus 1x is 2x, so we really just have a 2x there, plus 1. And it's over 9x to the 2/3. So now this thing is factored, we can play with it. Let me just separate that off a little bit like this. You know, these are separated off like this. Okay? We got this, this, and this. So this is the second derivative, factored and all ready to go. So now what we need to do is we need to say, where is the second derivative 0 and where is it undefined? Where is it equal 0? That's going to be when the top equals 0. And where is it undefined? That's going to be when the bottom equals 0. So we'll have to continue this on another sheet. So where's the top 0? Well, oh, by the way, there's actually something else I could have done here. I'm sorry. Look. See this factor of x to the negative 2/3? That's really downstairs as an x to the 2/3. So we have another factor of x to the 2/3 downstairs, and when I multiply x to the 2/3 times x to the 2/3, I add the exponents, I get x to the 4/3 downstairs. This negative 10 is still up there. This 9 is still down there. And we got a 2x plus 1. Right? All I did is I said this x to the negative 2/3 upstairs, the factor of it, is really x to the 2/3 downstairs. And x to the 2/3 times x to the 2/3 is add the exponents, get x to the 4/3 downstairs. So negative 10 is upstairs, 9 is downstairs, 2x plus 1. Now then, we can go to what I was saying up here. Where's the top 0? Where's the bottom 0? Well, the top is going to equal 0 when 2x plus 1 equals 0. So I'll subtract 1 and divide by 2, and that's going to give me x equals negative a half. And where is this thing going to be undefined? That's going to be when the bottom equals 0. The bottom is going to be 0 at x equals 0. Right? So now it's time to play this game where we do the intervals of concavity on the number line. So let's just take this over here so I can use my paper up a little nicer here. And I'm going to make a number line. I'm going to put, these are actually the critical values of f prime, if you think about it. And I'm going to put the negative 1/2 and the 0 on this number line. And now I'm going to choose values to the left, right? So I took the negative 1/2 and the 0, I stuck them on a number line, and now I'm going to choose my test values. Something to the left of negative 1/2, say negative 1. Something between negative 1/2 and a 0, say negative 1/4. And something greater than 0, say 1. Now I'm going to stick these into, let me see if I can just get this other sheet out of the way, because I think we're done with that for a minute. And we're going to stick these right into the second derivative. Here's the second derivative. So here's my test value over here. The negative 10, that's negative. 2 times negative 1 is negative 2. Negative 2 plus 1 is negative. The 9, that's positive. Now I'm sticking a negative 1 into this. Well, the third root of negative 1 is some negative number, and then a negative number to the 4th power is a positive number, and this is positive. Or you could have said negative 1 to the 4th is positive, and the third root of a positive number is positive. Either way, you're going to get positive. So we got a negative times a negative up top, which is positive. Positive times positive on the bottom is positive. Positive over a positive is positive. So what we found is the second derivative is positive to the left of negative 1/2. When the second derivative is positive, we're concave up. So now on to this next test value right here, negative 1/4. So I'm going negative 10, that's negative. 2 times negative 1/4 is negative 2/4, otherwise known as negative 1/2. Negative 1/2 plus 1 is positive. The 9 is positive. And now I'm taking a negative number to a 4th power, which is positive, and the third root of a positive number is positive. Another way to say that is I could have taken the third root first, the third root of a negative 1/4. The third root of a negative number is negative, and then the negative number to the 4th power is positive. So we got a negative times a positive up top, which is negative. Positive times a positive on the bottom, which is positive. Negative over a positive is negative. When the second derivative is negative, you're concave down, so this function is concave down on this interval between negative 1/2 and 0. Now we got to test our next value, 1. So the negative 10 is negative. The 2 times 1 plus 1 is positive. The 9 is positive. And the 1 to the 4/3 is positive 1. 1 to the 4th is positive. Third root of a positive number is positive. So you're positive. Negative times a positive on the top is negative. Positive times a positive on the bottom is positive. Negative over a positive is negative. So now we've seen then the second derivative is negative on this interval greater than 0. So it's still concave down. So now we got a lot of information here on this thing. Let's start putting it together. This function is increasing when f prime is greater than 1. And we can see it right off our first derivative test. It's increasing from 0 to 1. It's decreasing when f prime is negative. You can see it right off the sketch here. It's decreasing from negative infinity to 0. And it's decreasing from 1 to infinity. We've got a local max at 1, 3. This part's a little sneaky, but remember I said a little aside here that because of those negative tangent lines, the negative tangent line over here and the positive tangent line over here and this undefined derivative here, that the function looks like this. It does look like that, and it's not differentiable there. However, look, there is a local min there because the y value right there where my finger is less, locally, it's less than all the y values immediately around it. That's called a local min. Local minimum, right? They'll call it a relative minimum. A local min at 0, 0. So now we got to do our intervals of concavity, and we get that off the second derivative right here. So we're concave up from negative infinity to negative a half. Yeah, this one is definitely a little sneaky because of that. But it's true, you got to go through with what you see here. It's concave up on negative infinity to negative a half. And it's concave down. Here you got to be careful, okay? Because you want to kind of just say, well, look, it's concave down here and it's concave down here, so it's concave down from negative infinity to infinity. But at x equals 0, if you remember, that was a place where there's like something weird happening on this thing. It's doing this, right? So I know you want to just say it's negative, it's concave down on the whole thing, but the way it's actually said is it's concave down from here to here, and it's concave down from here on. So just like we're seeing right here, it's concave down from negative a half to 0, and it's concave down from 0 to infinity. Be careful about that, because if you put that it's concave down from negative a half to infinity, you're going to get it wrong. It's negative a half to 0, where there's like a weird little point, and then it's concave down, continuing from 0 to infinity, just like I wrote right here. So that's all the information about the concavity. Now it's time to get the sketch together. Now this one's a little sneaky. That's why I'm doing this, is because I want to have some, more challenging examples. So let's get the sketch on this one. Here's an x-axis. Here's a y-axis. We got that at 0, 0, that's where it was coming down like this. And we got at 1, 3, at 1, 3 is where it had a local max, right? We had a local max at 1, 3, a local min at 0, 0, and there was like a little pointy weird thing happening there. So this thing is going to be coming down. There's a local max right here, so it's going to be coming like this. Somewhere there's an x-intercept here, and you could find that by taking f and setting it to 0. There's an x-intercept. And this video is getting a little long, so I'm going to say if you really needed to find it, you would just set f to 0. In other words, you'd say 0 equals 5x to the 2/3 minus 2x to the 5/3. And this wouldn't be too hard. You'd factor out the x to the 2/3, and you'd have a 5 minus 2x to the 3/3. because the 3/3 would add with the 2/3 to make this x to the 5/3. So in other words, it's going to happen at x equals 0. And where does 5 minus 2x, sorry about that, but it's back on the screen now. Where does 5 minus 2x, where does 5 minus 2x equals 0? That's going to happen where 2x equals 5. That's going to happen at x equals 5 halves. So you can bet this x-intercept right here is at x equals 5 halves. And this x-intercept here is at 0, 0. And this is what it's looking like. Now this is where things get a little sneaky, right? It's concave up from negative infinity to negative a half. But also it's increasing, or let me say it like this, it's decreasing from negative infinity to 0. So it's decreasing all the way, but somehow it was concave up to the left of negative a half. See how it's concave up to the left of negative 1/2? So it must be looking kind of like this. It goes like this. Right? Let me just put the 1/2 like right here, the negative 1/2, because that's a little bit, just because that's the way it kind of sketched for me. Right here, this is negative 1/2. So let's make sure this is what we think it should be. Is it concave up from negative infinity to a half? Yup. From negative infinity to negative 1/2? Yup. Is it concave down from negative 1/2 to 0? Yup. And from 0 to infinity? Yup. Is it increasing from 0 to 1? Yup. Is it decreasing from negative infinity to 0 and from 1 to infinity? Yup. Does it have a local max at 1, 3 and a local min at 0, 0? Yup, yup, yup. Let me get all that on the screen in case some of that wasn't on the screen for our discussion. But it's all right there. A very, very good problem. 32 minutes in.